Well, hello again. Back, and today I've got a topic that we haven't yet covered, and that is MIDI. We'll do a quick video today. We'll just touch on high-level overview of what MIDI is. Then we'll figure out how to write some circuits to handle MIDI input, MIDI output. And then we'll configure the 47 effects library for the Arduino framework. And we'll get it to work with a STM32 Blue Pill using PlatformIO. Okay, let's go ahead and dive right in. Okay, so MIDI, or MIDI, or musical instrument digital interface, is a technical standard that facilitates communication between electronic instruments and computers and a bunch of other devices. MIDI was introduced in '83. It basically standardizes the communication protocols that allow all of these devices to talk to each other. Prior to that, a lot of manufacturers, they all had their own standards. And so trying to sync things, something that Roland, might have done with something that Cork was doing was almost impossible. But, a bunch of them got together and they came up with this standard. And of course, as we know now, it revolutionized the entire electronic music industry, making it a lot easier for musical devices to communicate with each other. Integrating MIDI into a Eurorack environment offers quite a lot of expanding possibilities, right? It allows us to bridge that gap between the analog world and the computer world. We can use it to sync our Eurorack gear with our drum machines or our computers. And so I think that it is essential for us to cover this topic. So hardware setup. So MIDI utilizes a 5-pin DIN connector. And out of those 5 pins, it really is only using 4 and 5. The shield, it is only connected typically on one end. And the whole reason for this is that the standard calls for a method for completely decoupling circuits, right? This is so that there is no electrical connection that is actually shared between the devices. So we're going to be using 2 pins. One of those pins is typically connected to a voltage source, a current source, and the other one is where the data is read. Over the I don't know, I would say probably the last 10 years or so, there's been quite a big trend to use smaller connectors because, it's a lot easier and a lot more compact as well. So devices like drum machines and some smaller, like the boutique series of synthesizers, they all utilize 3.5 millimeter jacks. And unfortunately, similarly to what was happening before the standard was introduced, companies decided to do it themselves. So we ended up with 3 different standards utilizing 3.5 millimeter jacks. 2 of them use TRS. TRS stands for tip, ring, and sleeve. And one of them is just a TS, or tip and sleeve. And out of those, so the TRS-A is typically, it's this one that we see right here, where the source is in the tip and the sync is on the ring. TRS-B reverses those two, and TS uses the only more of a mono jack. Anyway, which one we use is going to be depending on the hardware that we are going to be connecting to, right? So If you have a Korg device, then you're likely going to be using TRS-A. If you have like an Arturia device, you're probably going to be utilizing TRS-B, right? I'll leave some links in the description for you guys to go and check out and, you know, do more research on that. Okay, so let's talk about the circuit setup. Output wiring is actually really simple. The main thing to note here is the impedance that is needed for the communication. You know, it's really dependent on the device that you're writing the circuit for. What I have here on the board on the screen was actually something I took from the Teensy website. I've tested these values with Arduinos, with the Blue Pill, with Teensys, and I've never had any issues. So this is definitely something that at least I use in my setups, and I encourage you guys to try it out as well. The source, it just goes from a power supply. I typically just take it either from the microcontroller or from whatever regulator I'm using to power the microcontroller. If you have a microcontroller that operates in 5 volts, then 220 ohms is the impedance that you're likely going to be using. And if you have one that is operating at 3.3 volts, which is what we have today, we're going to use a 47 ohm. And this is for output, right? Now the sink just gets connected to the microcontroller pin, and that pin is a serial pin. Okay, the output wiring is a little bit different. The standard calls for complete decoupling of the two circuits. So in order to do this, we utilize a device called an optocoupler, which is this thing which I'm showing in the screen right now. So let's see if we can figure out what's going on here. So source, of course, is coming. We know that, you know, this represents the output that we showed previously. So source is 5 volts. The sink is the microcontroller. So the microcontroller is deciding when we will be conducting. So current is going to flow through this 220 ohm current limiting resistor, which will then light up this LED, which is inside of this optocoupler. This, by the way, this diode right here, this is called the flyback diode in this configuration, and it's typically just placed here for protection against current spikes so that we don't blow up the LED in here. On the other side here, this thing that you see here, this is called, this is a phototransistor. This is a transistor that has a light-dependent sensor at its base. So whenever it detects light, it will start conducting. This setup right here is followed by a second transistor. Whenever you see 2 transistors, one with the emitter connected to the base of the next transistor, that is called a Darlington pair. And that is a form of non-inverting amplification that happens. So basically what that means is that whenever this LED lights up, this sensor will start conducting. And so if this is conducting, then this will conduct. And so if we look at where the pin from the microcontroller is connected, this is the input pin on the microcontroller. It is connected through a pull-up resistor, right? Which is just going to ensure that whenever this is not conducting, the serial pin here is going to see a high state, right? Which is 5 volts. Logic state high, 5 volts. But whenever this starts conducting, it's going to pull that connection to ground, so the pin is going to see 0 volts. The resistor value here is important. It influences the performance of the digital communication at the input pin here. Again, the values I pulled from the Teensy website, and I know they work with both the Blue Pill and Arduino and Teensy. So yeah, for 5 volts, 270 ohms, for 3.3 volts, 470 ohms should do the trick. Yeah, so that's about it for this. Let's move on to the next topic. So the MIDI library we're going to be using today is one by 47FX. It is a library for MIDI communication written for the Arduino framework. Now, I was not able to get it to install from the PlatformIO plugin manager or library manager. Instead, what I had to do was clone the repo inside of the lib folder, and things just work. Another thing you could do is you could download the repo and unpack it into that folder as well. Once I have it in the folder structure, then I am able to include it into my sketch, and then we can initialize it and use it to receive and send MIDI data. It's really quite straightforward. So rather to spend a whole bunch more time here, let's just move on to VS Code and show you a simple example of how this is done. Okay, so let's walk through the code real quick and just see what I have here. So first, as you can see here, I have extracted the MIDI library inside the lib folder. I just checked it out, checked out the repo. And as I was saying before, that there is this examples folder, which is really useful. It has a lot of good examples with how to set it up and you know how to use it. So I encourage you guys to check this folder, this example folder out. Here's my PlatformIO, just INI, because I want to explain a few things. So I am using this Blue Pill, and this Blue Pill, in order to get the serial console to work, let's bring up the other camera. Yeah, so in order to use the serial console to work, I need to use this device here, right? And so this device is connected right now to the hardware serial 1. So in order on the Blue Pill to get hardware serial 2 to work, I have to enable it first, okay? So we're gonna be using this hardware serial 2 for MIDI and the default one for our serial monitor. The rest of the stuff is just setting the board for my for this project and the framework, which is Arduino. That's what we've been using, and then that's the port of this thing. Okay, so let's look at main.cpp. In order to use it with this other on this other serial port, the first thing we got to do is we got to create the serial MIDI device. Okay, and we do that with this command here. I mean this line of code here. Once we have that, then we can create the MIDI instance by passing it the serial 2 object that we created up here. Then the rest is the same, right? So we're going to be setting up for this example. All it's going to do is it's just going to listen to note events, and then we're going to print them to the serial monitor. Okay, that's the first thing we're going to do. And we're going to do that by making use of a callback function. This way, our loop can only contain the read function, and then the object itself will have functions that we pass it to handle the note devices. And there's various ones, so definitely check the example folder for the documentation on the MIDI library because it's quite extensive. A lot of the callback functions work essentially the same way, so you'll be able to figure out once you understand this, right? So we're going to pass this function that we're going to create, and it is expecting a MIDI channel, the pitch or the note, basically the note value, and then the velocity, right? And that's going to be passed onto this object, and then we're going to use that information to do whatever we need to do. So in this case, all I'm really doing is just printing it straight into the serial console. In the MIDI setup, we're going to configure MIDI. This is for my serial monitor, my serial console, or serial monitor. So we're going to configure MIDI. Right here, I'm setting it to listen to every MIDI channel, all 16 of them. And then here is where I'm setting my handler, right? My function. I'm saying, hey, set this handle node on. Here is the function. That's the function that I'm passing, right? And so in MIDI loop, all I'm going to do is every time we iterate through that loop, the main loop of the function of the program, we're going to read MIDI messages, okay? And so yeah, let's go ahead and try this out. Now that I have my serial monitor open, let's go ahead and press play here, and we should see some messages come through. So let's stop that. Here's an example of how we would send notes. We would use the send note on and send note off functions of the MIDI library. And the function itself is just expecting the note, the pitch or the note value, a velocity, and then a channel. What I'm doing here, we're gonna send the note on channel 1, and then we're gonna send a note on channel 2, and then we're gonna send a note on channel 3. And so what we should see here is node 1, node 2, node 3, and there's some delay on each loop. So I'm gonna make sure there's nothing playing in here. I'm gonna make sure that I am plugged into the MIDI in jack. And then let's load the sketch. And there are our lights. MIDI integration with microcontrollers offers vast creative potential. Incorporating MIDI with DIY projects enhances flexibility and connectivity, allowing you to integrate your sketches with other music gear, computers, or, as we'll see in the next video, modular systems. So with that, we've come to the end of this video. If you found this information useful, go ahead and hit that like button. And if you want to see more, please consider subscribing, because seeing that subscription count increase really encourages me to keep making videos like this in the hopes that it will help others. Until then, stay curious, and we'll see you later.